So now let's take a look at the network. This is a simple DC network combination circuit problem, and I pulled the network from the online physics lab, which is an excellent resource. This is our circuit here. It's a combination circuit. It's starting out with a resistor, and then we have a parallel branch, and the bottom parallel branch has another parallel branch in it, and then it comes back to a junction point. The top parallel branch has another parallel branch in it, and the top branch of that mini parallel branch has two resistors in series, and then that particular parallel branch, that mini one, is in series with another resistor, and then they come back to the main junction point. So we've got a lot of complications going on here. To do this circuit, what we want to do is reduce it to its simplest point. So we want to be able to say if we have point A and point B, this entire complex circuit can be replaced by one simple equivalent resistance. We want to find out what that equivalent resistance is. Once we find out the equivalent resistance for the whole total circuit, then we're going to work backwards and use this information to find out what the current is and the voltage drop is for each resistor. That's our plan of action. This is going to get real complicated, so to help simplify things, I've got here a chart. Okay, it's called like a RIVP chart. Not rest in peace, but RIVP, rest in very good peace. Okay, and what we're going to allow that to, what that's going to allow us to do is keep track of all of this information as we find it out. The way I'm going to use this chart is I filled in all the resistors that we have. We have 1 through 7 resistors. And then I also added RC, where RC stands for the total circuit resistance. RE, or equivalent resistance, would be fine too. I'm going to use the values that was given to me in the problem to fill in these resistances. Okay, so all I did was get the values that were given to me in the initial problem and put it in the chart. So I've got the resistance values for all 7 of my resistors. And then it also told me at the beginning of the problem that the voltage supply is going to be supplying 40 volts when it gets hooked up. So I know the total circuit voltage, and I know individual resistance values. My goal is to reduce this to one resistor, and I'm going to start on the inside. And the first place to start at would be in one of these two parallel branches. I could either do the bottom branch or the top branch. I'm going to go ahead and start with the bottom branch. So in my bottom branch, I have R6 and R7, and they're in parallel. So I'm going to use the parallel resistance rule to find out what the equivalent resistance for those two resistors are. So looking at the bottom branch equivalent resistance, the formula is 1 over RT equals 1 over R6 plus 1 over R7. Substituting my values in, I get 1 over RT is equal to 1/9 plus 1/38. You could try and find least common denominators, but with numbers like this, it's easiest just to plug it into your calculator. Plug it into the calculator and add it, and you get 1 over RT is equal to 0.137. And I just want to point out here, I tend to use RT instead of R equivalent. It's more common to use R equivalent, but I just use RT. In order to actually get the RT, you're going to have to take 1 over 0.137, or what you're basically doing is taking 0.137 to the -1. And when you do that, you get that the equivalent resistance for that parallel branch is 7.28 ohms. What that means is that we could take out this parallel branch and replace it with one resistor that had a resistance of 7.28 ohms. And so what we're going to do is redraw the circuit, and we're going to actually do that. We're going to redraw it with one resistor in place of that parallel branch. So I've redrawn the circuit, and where that blue box is where the old parallel branch was. And I'm replacing that parallel branch, the bottom branch, with one 7.2 ohm resistor. So what's the next thing to take care of? Well, we've done this branch. Before we can combine both branches, we've got to simplify this little mini parallel circuit right here. To simplify the mini parallel circuit, we first have to simplify this top branch of this parallel circuit. The top branch has two resistors in series. So we're going to take those two resistors and replace them with one equivalent resistor. So I'm replacing the top branch of this small parallel circuit with one equivalent resistance. And since they're in series is very simple. The general formula would be RT equals R2 plus R3. R2 has a value of 1 ohm, R3 has a value of 10 ohm, so the equivalent resistance, or the total resistance of those two resistors, is just 1 plus 10, or 11 ohms. So I'm going to redraw my circuit, and when I redraw it, I'm going to replace these two with this one resistance. So now I took the top branch of this small mini parallel branch and replaced the two separate resistors with one equivalent resistor of 11 ohms. What am I going to do next? Well, now I want to take this whole parallel branch. What am I going to do next? Well, now I want to take this parallel circuit right here, these two branches, and replace them with one resistor. So I need to find the equivalent resistance of that boxed in area. So, having done the math, the equivalent resistance of this parallel circuit, the one that's boxed in yellow, the general equation is 1 over RT equals 1 over 11 plus 1 over R4, or 1 over RT equals 1 over 11 plus 1 over 6.31. 1 over RT equals 0.249. Do the big flip, or take 0.249 to the -1 value, and we get RT is equal to 4.01. The part of the circuit that's boxed in yellow, those two resistors, could be replaced by one resistor of 4.01 ohms and would act the same. So I'm going to redraw my circuit. So again, that yellow boxed in area has been replaced by an equivalent resistance of 4.01 ohms. So the circuit is looking simpler and simpler. Okay, our circuit is getting simpler every time. Now we have the bottom branch with only one resistor in it. The top branch of this parallel circuit has two resistors in series. So we want to find the equivalent resistance of these two resistors that are in series, or another way of saying it, the equivalent resistance of the top branch. Series circuits equivalent resistance is really easy to do. So the general equation would be RT equals 401 plus R5, or RT equals 401 plus 2, or RT equals 6.01 ohms. So I'm going to redraw my circuit, and I am going to replace these two series resistors with one equivalent resistance. The equivalent resistance of this parallel circuit is 1 over RT equals 1 over 6.01 plus 1 over 7.28, or RT is equal to 3.29 ohms. So I can replace that parallel part of the circuit with one resistor, and I redraw it, and I now have R1 is hooked up in series with a resistor of 3.29. And of course the next step is to simplify these two resistors, and these two resistors are in series, so the equivalent resistance is just RT equals R1 plus 3.29, R6 plus 3.29, or RT is equal to 9.29 ohms. So I redraw the circuit, and I have the circuit with one resistor, which I said was my goal. What do I do now? Since we know the total resistance, 9.29 ohms, and since we were given the total voltage of 40 volts, we can find the total circuit current. So 40 divided by 9.29 using Ohm's law gives us the total current for the circuit is 4.31 amps. Since we know the current, we can find the power used by the whole circuit. So power equals current times voltage, so the power of the whole circuit is the current of the whole circuit, 4.31 amps, times the voltage of the whole circuit, 40 volts. So the power is 172.19 watts. Before we get too excited, I'm going to fill in that table with some of this information. So I went back up to my table and I said I know what the total circuit current is, 4.31 amps. I know what the total circuit power is, 172.4 watts. That's all I can fill in yet, but it's going to start. Okay, if our total current is 4.31 amps, that means going down this wire, we have 4.31 amps of little electrons. If I go to my next simplification, my next drawing, so I'm going backwards now, that means going through resistor 1, which is in series, I have 4.31 amps. The electrons don't have a choice of where they're going, so they all go through this resistor, and then they go through this equivalent resistance, and then they go to the very end. So, according to Kirchhoff's laws, they use up some of their energy in resistor 1, and they use up the rest of their energy in the next equivalent resistance, but all of them go through there. So now I know what the current is through resistor 1. And if I know what the current is, and I know the resistance, I can figure out what the voltage is across resistor 1. Okay, so because it's in series, the current going through resistor 1 is 4.31 amps. That voltage, V equals IR, the voltage across resistor 1, or the voltage drop, is 4.31 times 6, or 25.86 volts. But we can figure out the power also, because power is just current times voltage, so the power is the current, 4.31 amps, times the voltage, 25.86 volts, and that gives us 111.46 watts. So I'm going to fill out my table with that information. So for my resistor 1, I've got the current filled in, the voltage filled in, and the power filled in. Now let's go back and do some more. All right, I've got 4.31 amps of electrons marching through resistor 1, and then they hit point B, and they get to make a choice. Some of them are going to go up, and some are going to go down. And they're going to go through this equivalent resistance, they're going to go through this equivalent resistance, and they're going to join back up at point C, and they'll all go marching on from there to go back to the battery. We don't know how much goes through each branch, but we do know that the voltage drop from B to C is the same. So I'm going to use their equivalent resistance to figure out what the voltage drop is across this branch. So in this drawing of the circuit, we said that all of the electrons that go through resistor 1 go through this equivalent resistance. So to find out what the voltage drop in this equivalent resistance of 3.29 ohms, just that guy, I'm going to take its current, 4.31 amps, times its resistance, 3.29. That gives me a voltage across this equivalent resistance of 14.18 volts. Going up here, that means from point B to point C, the voltage drop across point B to point C is 14.18 volts, because this right here is point B and this right here is point C. Okay, the voltage drop from point B to point C is 14.18 volts. The current in the top branch is simply the voltage drop, 14.18, divided by the equivalent resistance of the top branch, which is 6.01, which gives us 2.36 amps go to the top branch. The current in the bottom branch, 14.18 divided by 7.28, are 1.95 amps. That means when the electrons get to point B, 2.36 amps go up to the top branch, and 1.95 electrons, or amps, go to the bottom branch. So now we know what the current is in each branch. So now we're going to take that information and do a little more. So coming out of the battery, we have 4.31 amps marching through resistor 1. Of those 4.31 amps, 2.36 take the top branch and march on. Now, we don't really want to work with this equivalent resistance yet, so we're just going to let them march through that equivalent resistance. It's in series, and those 2.36 amps march on in series, so all of them go through R5. So now we know what the current through R5 is. If we know what the current is and the resistance, we can find the voltage drop and the power. So let's do it. So I know 2.36 amps are marching through those two resistors, which means R5, the voltage drop is 2.36 amps times 2 ohms, or 4.72 volts. The power is IV, so the power is 2.36 amps times 4.72 volts, which gives us a power rating of 11.14 watts. I'm going to fill in my chart up above. Next I'm going to do is find the voltage drop across this equivalent resistance here, because I know what the current is and I know the resistance. So I'm going to use that information to find the voltage drop across that. So that tells me that the voltage drop across this 4.01 equivalent resistance is 9.46 volts. Why do I care about that? Because if I go up here, that equivalent resistance was for this yellow boxed in area. So the voltage drop for this yellow boxed in area, so we call this point to this point, is equal to 9.46 volts. But since it's a parallel branch, that means that the voltage drop from right here to right here is 9.46 volts. And while the electrons have a choice which direction they go, the voltage that they start out with is the same as the voltage they end up with, no matter which way they go. So I can find out how many electrons go marching through R4 by using this information. And I'm going to go ahead and do that. So I find the current going through resistor 4. 9.46 volts divided by 6.31 ohms gives me a current of 1.5 amps. Once I find the current, I can find the power. So the power across R4 is 1.5 amps times 9.46 volts, or 14.19 watts. And of course, I fill that information in on my table. moving on, we have R1 taken care of. We have its power and its voltage drop. We have R4 taken care of, its power and its voltage drop. We have R5 taken care of, its power and its voltage drop. So how about the next thing we look at is this equivalent resistance up here, this 11 ohms on the top branch. So again, we know the voltage drop from the one junction point to the other junction point is 9.46 volts. So using this equivalent resistance of 11 ohms, I get that the current going through the top branch is the 9.46 volts divided by 11 ohms, or it gives me 0.86 amps. That means 0.86 amps of electrons choose to go up the top branch and march through that wire. So moving on up to this guy, that means that we have 11 that means that we have 0.86 amps going through resistor 2, and because it's in series with resistor 3, all the amps, all the little electrons that go through resistor 2 also go through resistor 3. So 0.86 amps go through resistor 3. So I know the current going through resistor 2 and the current going through resistor 3, so I can find the voltage drops across the individual resistors. Because of course they're in series and they use up some of the energy. R2 uses up some of the energy of each electron before those electrons reach R3. So let's do that. So using that information about current, we find the voltage in R2, the voltage drop is 0.86 volts, and the voltage drop for R3 is 8.6 volts. And once we have the voltage and the current, we can find the power. And so the power in R2 is 0.74, and in the power in R3 is 7.4. Those are both in watts. So of course I filled in my table. So I go to my table up here, and I've got R2 and R3 all filled in. So now I only have 2 resistors left to do to fill in the table. So if I go way back down to the beginning here, I calculated what the current in the top branch was, and it was 2.36 amps, and we used that. And I calculated what the current in the bottom branch was, and that was 1.95 amps. At the same time, I calculated what that voltage drop was from B to C. So I'm going to take that information, go way back up here, and that means from point B to point C, I have a voltage drop of the 14.18 volts, and marching down, see if we have like 4.31 amps coming from point A, marching through resistor 1. Some of them take the choice to go up here, and we have the others taking the choice to go down here. And the ones that take the choice to go down there was that number we just said. So we're going to use that number to find the voltage drop across here. Oh, but I don't need to. I know what that voltage drop is because I just said it. So the voltage drop from this point where it breaks off into 2 branches to this point where it recombines is 14.18 volts. We have 14.18 volts going between those two. And it's the same voltage drop for both R6 and R7 because they're in parallel. So I'm going to calculate their individual currents and their individual powers. So using that voltage drop information, and of course the resistance that was given, we find the current going through R6 is 1.58 amps. And once we have the current, we can find the power. The power for R6 is 22.34 watts. Likewise for R7, taking 14.18 divided by 38, we get a current of 0.37 amps. And the power for R7 is 5.29 watts. Take a look up at my table, and all the spots are filled. So you can take this table now, go to the questions on the page, and you can answer all the questions using the numbers in the table. Are you going to need all of the numbers for every question? No, not necessarily. Did you need to figure out all of the numbers in order to answer all of the questions? Yes, you did. Maybe you didn't need all the powers, but they were easy enough to calculate. So, in retrospect again, what did we do? First, we took this very complex combination circuit and reduced it to its simplest total or equivalent resistance. So I went step by step and simplified the diagram and simplified the diagram and simplified the diagram and simplified it, and finally got to its simple thing where it was only one resistor. Once I found the equivalent resistance, I found the circuit current and the circuit power using Ohm's law and the power law. And then I went backwards. I went from the simplest to the next one and figured out the voltage drop and then the current and the power. And then I moved on and I figured out from here the current, and once I got the current, I got the power. And then I moved on up and did the same thing, found the current and the power. These guys were in resistance. Actually, I didn't find the current, I found the voltage drop. When two resistors are in series, because their current is the same, we use the current to find the voltage. When two resistors are in parallel, we use the voltage, because the voltage is same, to find the current, and then we find the power as a result of that. So we just kept working our way back up through the sheet to more complex forms of the circuit and more complex forms of the circuit, knocking out bit by bit every single resistor, so you finally had all the information for all the resistors as well as the total circuit. And that is how it is done. Thank you very much for your time.